Welcome. This is 49C2 particle displacement and gas pressure in sound waves. So we're looking at two things here. We're going to look at how particles are displaced from their equilibrium position and how the gas pressure changes as we cut our way through a sound wave. So if we look at this, we're going to show it diagrammatically. So on this side, I'm showing, if I can find my pen, I'm showing a plunger, like a piston which moves backwards and forwards. And this is a tube of air, if you like. And we get these high compression regions here. And then we get in between, we get low pressure regions which are typically called rarefactions. And so we get compression, rarefaction, compression, rarefaction, compression, rarefaction. It's a bit like the crests and the troughs for a transverse wave. And we can say a sound wave consists of compressions and rarefactions, and then the variation of gas pressure from the equilibrium gas pressure is given by, and the way I've drawn it, so the pressure goes from equilibrium, goes to the top, that's where the compression is, and then we go to the bottom, and that's where the rarefaction is, and then we go to the top, and that's where the compression is. So the high pressure bits give us a graph which follows a sine curve. So we can say P max, the maximum pressure, that's like the amplitude, sine kx minus omega t. It's just like it did for the previous equations. And you can tell because it's a negative sign that this wave is moving to the right. But now if you ask yourself, well, hold on, how do we get this high pressure? Well, we get this high pressure clearly, if that's the point at which there's going to be a high pressure, then I get the high pressure because particles move towards it from both sides. And over here, if I have another high pressure, then particles move towards that from both sides. And then if I imagine the point where I have a low pressure, a rarefaction, how does it get so low? Particles move away from it. Now the particles in the middle, they stay, they just stay. Those particles don't move, these particles don't move, these particles don't move, these are moved away from, these are moved towards, these are moved towards. And so if we look over here, what we see is, to get this high compression region, let's get this compression region here, which is there, what happened is the particles to my left had a positive displacement, so they moved to the right, and the particles to my right had a negative displacement, so they moved to the left. Can you see that? So what I get, let me just clean this up a bit, what I get is two graphs. I get a pressure versus position graph and a displacement of the particles versus position graph. And one of them looks like a sine curve and the other one looks like a cosine curve. They're effectively 90 degrees or a quarter of a wavelength or pi over 2 radians out of phase with each other. And so we say, well, conceptually, if you look at the diagram, we see that the pressure wave is 90 degrees out of phase with the displacement wave. The displacement of a small volume element from the equilibrium position is then given by, so we get this, well, S max, the maximum displacement, cosine kx minus omega t. It's a cosine curve. So it kind of makes sense. In physics, I guess to be honest, I tend to talk more in terms of the pressure trace than the displacement trace. But I know my wife works in communication sciences and disorders where they do an awful lot with speech and hearing involves sound. Sort of speech actually, and they deal with different traces at different times. So what do I need you to know out of this? A couple of things. So let's have a look at this. What is the term for a high pressure region on a sound? Well, it's a compression. Sometimes called a condensation. I don't like to use that term much because it reminds us of the liquefaction of a vapor, and we're not liquefying anything. So I prefer the term compression. And if I'd said a low pressure region, I would have called it the rarefaction. And then the second part is recalling the notes. Which trace represents the graph of particle displacement versus position? And you can see that there's my compression and there's the maximum, so that's going to be a pressure. And if that's the pressure, this is going to be the displacement. So what am I looking for? Displacement versus position. This would be B. So two nice conceptual questions from this bit. There we have it.